Then we are ready to start. So my name is Andrew Fracknoy. I have the privilege of being the vice chair of the Board of Trustees of the SETI Institute, and I teach astronomy at nearby Foothill College. And it's a pleasure for me to welcome you to this session on kind of looking at forging a relationship between the very exciting results coming from the Kepler mission and the search for extraterrestrial intelligence. There are few things, I think, in current astronomy as exciting as the discovery of hundreds of planets orbiting other stars and our ability to characterize some of those planets in ways that even a few decades ago we would not have thought possible. So we have with us a number of distinguished panelists who will illuminate this topic. Our first speaker on my right, and I'm going to go and look at the little descriptions that they gave me. Doug Caldwell is a co-investigator on the Kepler mission and serves as instrument scientist. He's responsible for understanding and monitoring the performance of Kepler's single science instrument, the photometer. Doug has been working on transit searches since 1997. That makes him an old fossil in the field, before there even were transiting planets, or at least before we knew about them. That's Doug Caldwell. Next to Doug is Geoff Marcy. Geoff Marcy is one of the pioneers of planet hunting. He and his team found the first system of planets around another star, Upsilon Andromedae. They also found the first Saturn-sized planet, the first Neptune-sized planet, and the first transiting planets. He is also among the scientific leaders of the NASA Kepler mission and uses the large Keck telescopes in Hawaii to verify the planets found by Kepler and determine if they are rocky, gaseous, or weird, or maybe all of the above. All right. Seth Shostak, who probably needs no introduction to the SETI crowd, is on the SETI science team at the SETI Institute. He is a well-known author, host of the radio program Big Picture Science, columnist for the Huffington Post, and the public scientist for the SETI Institute. Seth is the person who most ably conveys the science that we do to the public. And lastly, Martin Still is director of the Kepler Guest Observer Office. He is also an astronomer with interests in a wide range of fields, not only exoplanets and what we learn about them, but also black holes, gamma ray bursts, binary stars that contain squozen objects, and other strange things in the universe. So I'm delighted to welcome the panel. And what we're going to do now is I'm going to ask each person on the panel to say a few words about this issue of the Kepler mission, what it does, how we're discovering planets elsewhere, and then in Seth's case about SETI and what the SETI mission is. And then we're going to look at how we can combine the work of Kepler with the mission of SETI. So let's begin with Doug.
Okay. So I'll tell you, in case people don't know, I've been living under a rock for a while, what the Kepler mission is. It's an experimental band from Southern California. Oh wait, no, that's the other Kepler mission. They're in the back. And you probably heard them last night. The Kepler mission is a mission launched by NASA in 2009 to search for other planets. In particular, its main goal was to characterize or measure the frequency of planets that are in positions around their stars like the Earth so that they might be habitable. Prior to that, there were a number of known planets, many of them found by Geoff here, but we weren't getting down to the very smallest sort of Earth-sized planets, and so that's what the Kepler mission was designed to do. And it's conceptually it's very simple, which is why I like it, I can understand it. It's basically a digital camera in space that's taking the same picture over and over again for originally 3.5 and now hopefully 7.5 years of this set of something like 170,000 stars that we're actually looking at. There's several million stars in the field of view. We ignore most of them. And what we do is we take this picture, we actually take it every 6 seconds, but we bin them together for about 30 minutes. Then we save the stars that we're interested in, and every month we send that data down to the Earth and search for slight dimming in these stars as a small planet passes in front of the star as it's orbiting. So the Kepler mission is looking for transits. If you were lucky enough, hopefully lots of people got to see the transit of Venus last week, or 2 weeks ago, I guess now, 3 weeks ago. And if you missed it, you'll have to wait for 100 and some odd years to see the next pair. But it was very exciting, but it was I saw it without any real magnification or telescopes, and it sort of drove home how difficult the job Kepler's doing is, because it was hard to see with just your eyes. You could see it, but and Venus, because we're much closer to the Venus-Sun system, its projection was much bigger than what it would be if we were very far away. So it's even harder, and so that's the kind of thing Kepler's looking for. We don't resolve the star image, of course. We just measure the brightness, and if a planet goes in front of it, we can see it dim for a little while, and hopefully determine based on that we're actually seeing a planet. And I think I'll pass on to Geoff to talk about some of the results. I guess the one thing is Kepler's been operating in space for about 3 years now, and we just recently got a mission extension from NASA to operate another 4 years. So hopefully we'll be taking data successfully for about 7 years total, 7 or 8 years.
That's right. I'm Geoff Marcy, and I'm really delighted to be here, and I'm amazed to see so many people here interested in SETI and also the planets being discovered by the Kepler Space Telescope. That the planets are offering us some remarkable news about the prospects of the abodes for life elsewhere in the universe. And I thought I would focus my attention on what Kepler is telling us about habitable planets that we didn't know beforehand, and information that bears directly on the search for life in the universe as well as intelligent life. And it's very hard to know where to begin, because Kepler has found nearly 3,000 planets so far. We haven't verified all of them, but most of them are real planets. And among those 3,000 planets, we find some that are the size of Jupiter. Some of them are orbiting close into the planet, to the star. Some are orbiting far. We find planets the size of Saturn, of Neptune, and then, quite amazingly, hundreds and hundreds of planets are being found by Kepler, as Doug described, that are the size nearly that of the Earth. Some of them are 1.5 times the size of the Earth, some of them twice the size of the Earth. Some of them are smaller than the Earth. We have something like 50 or so planets smaller than the Earth. And so we're beginning to discover with Kepler the full range, the diversity of planet sizes, and also orbital distances from the host star. And of course, orbital distance determines the temperature of the planet, especially when you fold in the greenhouse effect. With all of that diversity and all of these planets, I wanted to give you a message in just a minute or two here, what I think is most relevant to SETI. And I thought very hard about this, because most of you know already that Kepler is designed, as Doug mentioned, to find Earth-like planets. Frankly, we don't even know what an Earth-like planet is. What are the properties of our own planet Earth that render it Earth-like? Is it the composition of the atmosphere, of the oceans, the plate tectonics? Is it the core, the mantle, the presence of the moon, Jupiter not too far away, and so on? We don't know what an Earth-like planet is if it slapped us in the face. But with that holy grail, finding other Earths or nearly Earth-like planets in mind, there's a discovery that Kepler is making right now that I think is as profound, or maybe more so, than the discovery of an Earth clone. And that discovery is this. Kepler has now found several hundred planets. In fact, the vast majority of the planets have sizes between that of the Earth and 2 or 3 times that of the Earth. 1 to 3 Earth diameters as we measure them from the amount of dimming of the star as the planet crosses in front. The bigger the planet, the more the star dims when the planet crosses in front. So we measure the sizes of the planets quite incontrovertibly, and amazingly, and we didn't expect this before the mission was launched, amazingly, the vast majority, 2/3, 3/4 of the planets, are between the size of the Earth and 2 or 3 times the size of the Earth. What are these planets that are frankly smaller than Uranus and Neptune, but a little bit bigger than the Earth? Well, we have some very good clues of what they are. We have been able to measure the density of about 15 or so of these planets that are nearly the size of the Earth. And their densities come out to be nearly 1 gram per cubic centimeter. And you might be saying, uh-oh, I remember from high school chemistry, I'm supposed to know what 1 gram per cubic centimeter means. I'll remind you, if you've forgotten, that's the density of water. Water has a density of 1 gram per cc. And when you find planets with a density of 1, you know for sure that they're not pure rock, like the Earth. You also know that they're not made of pure gas. They're too small, they'd be too fluffy if made of gas. The density would be lower than 1. These are planets that almost certainly, and we have some ancillary evidence to point in this direction, these are planets that have a large component of water. They might be 30% water, 50% water, 70% water, the rest being maybe rock and maybe some gases. But predominantly they are indeed composed almost certainly of water. And I'm leaving out other details of other planets that have been studied carefully, both discovered by Kepler and maybe by other teams, where we actually have detections of the water spectroscopically. So what this means for SETI is this. When you look up into the night sky at the thousands of stars your naked eye can see, and of course you know that that's a small fraction of the hundreds of billions of stars that inhabit our Milky Way galaxy, what you know when you think about the stars at night is that a vast majority of those stars have these remarkable planets. They're something like the size of the Earth, a little bigger than the Earth, some of them may be smaller, but there must be large amounts of water. And we all know what's special about water with regard to SETI. Water is the key solvent of biochemical reactions. It's the cocktail mixer that allows the carbon-based molecules to break apart, reassemble into other forms, amino acids, maybe eventually proteins, and perhaps, if you break them apart and reassemble them enough, into something like DNA. And so it's the liquid water on these hordes of planets that offer, I think, a real hope that there are planets out there which have developed replicating molecules like DNA, maybe not exactly DNA, some other replicating molecule. Those replicating molecules will compete for resources, for the energy, for the other atoms, and eventually that competition will lead to surviving molecules that outcompete the others, and voila, you have Darwinian evolution. The successful molecules will move on, presumably develop a lipid-based shell that we would call a cell membrane, and voila, you have the first signs of life. And so I think what Kepler has discovered is widely appreciated. It's these very likely water worlds as a predominant type of planet in the universe, water worlds that can certainly serve as the petri dishes for life as we know it.
Before we go to Seth, let me just encourage people, if you have a seat next to you, would you raise your hand? You have an empty seat. So people in the back, if you're just scouting out whether we're interesting, you can stay back. But if you actually want to sit down, there are seats available wherever you see a raised hand. Come on up and join the group. And I'm going to turn things over now to Seth Shasta.
Thank you, Andy. I have to say I feel humbled sitting here on this panel, although as somebody pointed out in the audience, Seth, you should feel humble. But I mean, so sitting next to Geoff Marcy, who has found more planets than any other hominid in the history of the planet. And it's sort of like discussing the future of psychology next to Dr. Phil, I suppose. Anyhow, in terms of, I hope you won't take umbrage at that, Geoff. let me just say some obvious things about how Kepler will affect SETI. To begin with, if you look at the distribution of planets as a function of star type, in other words, which kinds of stars have which kind of planets, if it turns out there's some strong relationships there, well, that's good news, because now you can say, all right, we're going to look preferentially at this kind of star rather than that kind of star because they're more likely to have planets that might be habitable. So that kind of information would be very useful. One thing that's come out of exoplanet research recently that I find personally very encouraging is the fact that even small stars, red dwarf stars, but small stars, smaller than the sun, seem to have planets that might be habitable. And that's good news because there are 10 times as many of those as there are stars like the sun. So that's one obvious thing. But the second thing, and this is actually maybe the trump card in all this, is the result that planets are very commonplace, right? Before 1995, we didn't know that. Now, I asked Geoff actually on the phone, I don't know if you remember this, Geoff, maybe 6 months ago, something like that. I said, Geoff, if you had perfect instruments, what fraction of stars do you think would show planets? And I think he said, oh, maybe a half, maybe 3/4. Now, to an astronomer, a half is the same as all, right? In astronomy, pi is equal to 1. So, I've been using that in talk. I say, essentially they all have planets, and there have been some papers published just in the past month that attest to this, saying that essentially all stars have planets. Okay. And by the way, keep in mind that, the majority of planets are not around stars at all. They're drifting off in space, probably having a very bad time. So the point is that in the Milky Way, the number of stars around planets is on the order, the number of planets around stars is on the order of 1 trillion. Not 1 trillion, something like that. Okay, so that's very good news for SETI. And in particular, what it suggests is we could look at anything and have a good chance that, that you're looking at a star system with planets. Now, the big question that Kepler has still not answered, and these guys will answer it, I don't know, Doug, within a couple of years, yeah, by 3:30. The question is, what fraction of star systems have planets that could indeed support intelligent life? And I don't think we know the answer to that yet. I don't know the smart money, which is to say these guys, probably are saying something is probably be between 0.01% and a few percent or something in there. And if it's as much as, 0.1%, that still means 1 billion habitable worlds in the Milky Way. And you can think that all of them are sterile except this one because you like to think you're the smartest things in the galaxy. My neighbors do. My brother does for sure. But that would make you a miracle. And one thing that, of course, astronomers are very leery of are explanations that suggest that we're a miracle. So that's the number that still has to come out of the Kepler mission, but I think it's likely to be encouraging. So let me just finish up by saying, what will we do on the basis of Kepler results? Well, we're already doing something. The Allen Telescope Array is being used, as you sit through this, to look at the planetary candidates in the Kepler field. In other words, we know that those stars have most likely planets. They're not unconfirmed, but we think that they may have planets. Okay, so that's obviously a better deal than looking at a random star, but apparently it's not that much of a better deal. And since they're far away, it might actually not be that much better a deal. But we are doing that. But I think that the real influence of Kepler on SETI is not what we will learn, but what it will encourage us to do. Because the big problem with SETI is lack of funding. There's no money, okay? And Kepler is a very high-profile science project that everybody can understand, and it's producing dramatic results, and I think that seeps down to the public to the point where they say, if they found so many thousands of, of planets, implying that there are millions or billions of planets that could have life in our galaxy, why aren't we looking for signs of cosmic company?
Just realized how incredibly hard it is to be fourth.
I asked you what order you
Yeah.
wanted. Now you see what I...
Yeah, can we swap? Can we start again? I came here last night to listen to the opening reception and listen to the keynote speakers, and there was one common theme running through all of their presentations, I thought, and that was that over the years, over the last few decades since the Apollo program, nations have, by and large, got out of the discovery business. And I think that comment was made more generally towards spaceflight and human discovery, because although it struck a chord with many things that we do at NASA and other space programs do, it didn't strike a chord to me as I am working within the Kepler project. The Kepler project is an amazing endeavor of discovery, which, the reason given is that people didn't feel involved. They felt out of touch with many of these old discovery projects. They were interested in seeing how they were going. They were interested to see what the results would be, but they didn't feel involved. And I don't think that's true with Kepler. I think people feel involved. They're always listening for the new discoveries, the new announcements, the new spectacular planets, the new spectacular planetary systems, and the new enormous sample numbers which come out once every 6 to 12 months. Where I think this also doesn't apply to Kepler is, whether you know it or not, the data which is being collected by Kepler is also being archived. And while a lot of that is currently firewalled, you can't see a lot of the most recent stuff, by October of this year, there will be no more firewalls. Kepler is changing. It's growing from a young mission where we were extremely nervous about the quality of the data and the quality of the results. We now have much more confidence in the data that Kepler is producing, and we have much more confidence in pushing this stuff into the public arena as early as possible. So what this means is that anybody sitting down in this room can go to this archive now, and especially after October, and find their very own planet. You don't have to be sophisticated to do this. In fact, there's at least one website open already, which is called planethunters.org, where you can go and eyeball all of the individual Kepler light curves. And indeed, people from the public have identified new planets or planet candidates within the Kepler field. And I believe this is just going to get bigger and stronger as time goes by. There are many of you out there who are computer savvy. You know your way around a Mac or a laptop. You can write your own code. You can do your own searches. Kepler is getting more and more into the business of large samples. As we announce newer and newer unique objects, the smallest planet, the planets within the habitable zones, first Earth-sized planet, first rocky planet, first multi-planet system. We're actually running out of firsts. And these announcements are going to probably get fewer and fewer, in my opinion. And Kepler's going to be more about putting together samples of planets. How many planets are Earth-sized? How many planets are in the habitable zone? So the job of getting excited and finding individual planets is probably more in your domain now than it is in ours. So I think in a very short space of time, guys like yourselves will be contacting NASA or the Kepler project or SETI or anyone else and saying, hey, look what I found. And indeed, you may be the guys that find that first Earth-sized object in a habitable zone around another star.
Well, thank you. Thank you, panel. The first thing I'm going to do, but we will ask the panel to respond, and then we're going to open things up to your questions. But I would just like to make sure that we define the term habitable zone so that people understand what that means and how it can differ from star system to star system. Who'd like to take that on?
Habitable zone. I mean, the term is fairly old now. It's sometimes called Goldilocks zone, and if you've gone to any of the major sci-fi films that have been released in the last month, you may notice references to some of the Kepler planets and also the Goldilocks zone. It was traditionally that distance from the star where if a planet were situated there, the surface temperatures would allow water to be not permanently frozen or permanently, boiled away into a gaseous state. The problem with that is they're twofold. One, of course, it depends a lot on the atmosphere. It'd be very cold here. You may think it is, but it would be very cold here if it weren't for the atmosphere, the greenhouse effect. So if you don't know anything about the atmosphere of the planet, you really can't say with a great deal of certainty what the temperature is. You can give some sort of limits. And the other thing, of course, is the discovery that there are 6 other worlds in our solar system that might have life, could conceivably have life, and none of them really, maybe Mars, but none of them is really in the habitable zone, as defined by what I just told you. The moons of Jupiter, 3 of the moons of Jupiter, 2 of the moons of Saturn may have reservoirs of liquid water that are kept warm by processes that are not dependent on the sun. Okay, so habitable zone has become, kind of a fuzzy term. Is that fair enough to say?
Okay, so now do the panelists have anything they want to add or amplify based on what the other panelists have said?
I'll say something.
Please.
I want to reiterate something that Seth mentioned, which is really the heart of the effort to do SETI research, and that is, frankly, lack of funding. One hates to bring up the old difficulty and challenge of getting money, but we live in an amazing era. We have extraordinary technology to sample the universe for signals that might be coming from intelligent civilizations. Might be radio waves, ultraviolet light, visible light, infrared light. There are many other techniques available sampling those parts of the electromagnetic spectrum, and maybe even other ways with looking for neutrinos or some other exotic particles. But the point is, with a relatively small investment of money, governments, various agencies could be funding extraordinary and unique SETI searches. The Allen Telescope Array is one example of a facility where for a few tens of millions of dollars, which is a small fraction of the cost of just one NASA space mission, for that tiny fraction of the cost of one NASA space mission, you could fund the Allen Telescope Array. And there are many other techniques, as I say, in other wavelength regions, other wave bands, to search for the prospective signals, maybe laser signals, who knows, from intelligent civilizations out there. And so I think there's a charge, a political, if you will, challenge for all of us. I certainly feel that challenge, which is to determine how to educate our government, other governments, space agencies, members of Congress, literally the people in the White House, to adopt Kepler, as Seth mentioned, as the sort of stepping stone, the platform, now that we know the planets are out there, to do the next step. And obviously the next step is SETI, and it's relatively inexpensive. But essentially right now we have almost no money to do SETI work. You can count the number of millions of dollars for the whole world that's going towards SETI, on one hand. So somehow we all of us in this room and everybody at this meeting, we have a real agenda item, a take-home homework assignment, if you will, and that is to somehow communicate to our governments the need to do this next step.
Anyone else on the panel wants to comment? Otherwise, we will throw things open to the floor. Mohammed, our exuberant volunteer, is going to walk around with a microphone because this is being taped for all those people who are not able to be here. We do ask you to wait until you get a microphone and then to speak into it clearly so we can record your question. And we have our first question in the back.
Yes, thank you. Were scientists surprised to find gas giants so close to stars?
We were shocked when the first one was found by the Swiss team led by Michel Mayor, 51 Peg B. I immediately was quite sure it was wrong, and we went up to the telescope ourselves and verified that the gas giant did exist, nonetheless blowtorched by the host star because of its proximity. One thing you all, I'm sure, immediately think about is how can the gas survive? Why doesn't it evaporate? Why don't the gas molecules achieve escape velocity under the extreme heat? And it turns out you can do the calculation. It's literally something you can do on a scratch piece of paper. Gas giants survive perfectly well, despite being just a few stellar radii from the stars themselves. They're hot, they're 2,000 degrees Celsius, but the gas survives and the planet remains intact.
I remember being in graduate school at the time and seeing this paper by Mayor and Kalo, and then this other one by some crazy guy, Marcy and Butler. I'm like, what? In grad school, you know everything. And I was like, there's no way, these people don't know what they're doing. And just as it went on, and all of a sudden, things more were found and more were found, it was really pretty eye-opening that it was a new thing. So.
All right. Who's got the microphone, please?
Yeah. Art Sussman. A question about, I'm trying to wrap my head around this idea of a planet that's mostly water. So in my mind, clearly it can't be all liquid water. I'm wondering what kind of percentages or whether some of it's frozen, what your thoughts about what that kind of planet is actually like. And then related to that, I know there's been some speculation about whether it's possible to have a marine-based intelligent technological, we know intelligent, yes, but technological organism, because the way water interacts with, silicon chips, for example.
Yep.
So thoughts about those two things, what that kind of planet would be like, and life on an essentially a water planet. Technological life on a water planet.
Shall I take a crack at this? Sure. So I'll start. So I have answers to both of your questions. What everybody here should keep in mind, it's really a beautiful concept. We know when you look at the periodic table of elements that there's a certain cosmic abundance of each one of those elements that pervades the universe. Hydrogen, helium, carbon, nitrogen, oxygen, iron, nickel, and so on. And it's true that the hydrogen and the helium are gases in the universe, even in protoplanetary disks. And so those gases can easily fly away, or they have to get gravitationally glommed onto a Jupiter somewhere. But what's left over are the following most common elements. Oxygen is the next most common. And then there's carbon and nitrogen and iron and nickel. And if you think about the hydrogen and the helium floating away because they're such light gases, what you're left with are the building blocks of our own planet Earth, namely silicon, iron, and nickel in the mantle and the core respectively, and certain amounts of the oxygen combined with the silicon so that we get silicates that makes up our mantle. The oxygen also combines with the hydrogen. So whatever oxygen you have, and it's the third most abundant element in the universe, it will glom on, that oxygen will glom onto the silicon, giving you silicates, of which the rocky part of the Earth is made, and the oxygen will glom onto whatever hydrogen is around to make H2O. And so actually it's very logical that the universe would have lots of planets, and moons, by the way, that are something like 50-50, water and rocky silicate material. It's just what you get when you dump the periodic table of elements into a beaker and mix them up. You get water and you get rock. And indeed, the outer half of our solar system consists of both planets and moons that are roughly 50-50, rock and water. So I think, in fact, the planets we're finding are sort of the logical kinds of planets with, a thick envelope of water. I've answered, that took a long time to answer that question, but I'll just quickly answer your other question. Water worlds that have something like 50% water will have these very thick oceans. And you might ask, could marine mammals of something like the marine mammals on the Earth develop intelligence? Obviously, the answer is likely to be yes, although remember the marine mammals on the Earth had to go to land first and then go back to the water. But I wouldn't be surprised if on a planet that had only water, you'd get pretty clever marine mammals. The tricky part with such a water world is developing technology. So when you talk about SETI, the I involves intelligence, And as Jill Tarter often points out, it's not just intelligence, because that can take a wide variety of forms. It's technology that really makes the difference. Only a technological civilization is one that we might be able to detect someday. So you might ask the question, on a water world with intelligent species living, swimming in that water world, would they be able to develop electronics, computers, and rocket ships? And there, I'm not sure. I don't know if anybody knows. There are some arguments that maybe on a water world, large platforms of seaweed would develop, and those platforms of seaweed would be miles long, and they would serve as the continents on which species could build on that dry platform the electronics and the computers and the rocket ships. But that's, of course, a little more speculative.
Yeah, I think the problem is metallurgy. A large part of it is you need probably metallurgy to do technology. And I point out that water worlds didn't work out so well for Kevin Costner.
No.
All right, do we have another question?
Yes.
Yeah.
You've spoken about Earth-like planets and that are rocky Earth-like planets. To what extent is Kepler able to analyze the atmospheres of those rocky Earth-like planets that you are talking about, being able to observe so far?
Sure, I'll start. Kepler doesn't know anything about the atmosphere directly, and basically what we measure is the amount of light that got blocked by the star. So we measure the relative area of the disk of the planet and the star itself. So the first information we get doesn't tell us anything. What can let us infer some things is if we get additional measurements, like radial velocity that'll tell us the mass, we can start to get an average density of the planet. And then we can say, well, if it's a very low density, like Jupiter, then there is most certainly some gaseous atmosphere. If it's a very high density, it might not have it. Or if it's very close to its star, it might not have an atmosphere. So at that point, we're appealing to models and our understanding of what these planets could be made of. But we don't directly detect the atmosphere. We can just determine essentially the average density and whether or not it's likely that there is something.
So just to argue with you briefly,
Yes.
that's almost true.
Excellent.
It's the exception is if the planet is very close to its host star and is cooked to incredible temperatures, or the atmosphere can be cooked to incredible temperatures. And there you see not only the transit of the planet in front of the star, but you see the occultation of the planet behind the star. It's that bright. And there you can actually use, it's model dependent, you can use theoretical models to actually limit some of the properties of the atmosphere of that planet just by how much it's being heated, how much brighter the object gets as it's approaching that occultation and the shape of the occultation itself. And that doesn't really help us in terms of civilizations and planets in the habitable zone, because these things do have to be close to their host stars, but that is the one exception that I can think of.
Wasn't there a planet discovered recently where they were able to tell the dust? There was a plume of evaporated dust. Is that real or not real? We heard a lot in the media, so let's hear from the experts.
I would hardly call myself an expert, but it's certainly one interpretation. And it is, of course, the most interesting interpretation. And we did get a lot of mileage out of that. And but the question is still there. It's an open book right now. It's a plausible thing.
Jeff, were you going to say something?
No,
about that?
I agree completely. There was a Kepler planet that one particular group has suggested, one interpretation, as Martin said, is that it's an evaporating Mercury-like planet. And frankly, there are other interpretations, and people are working very hard to see if that interpretation is right or if others are better.
Okay, good. Another question from the audience?
What new theories are there about planet formations on the inner systems now that you find gas planets near the stars?
New
I
theories
better
about
do this one.
Okay.
Yeah, let me repeat the question, actually, and it's a beautiful question. So the question is, what is the theory, the theoretical understanding of how it is Jupiter-like planets end up so close to their host stars? Did I capture your question about right?
Yes.
Yeah. So this is an extremely hot topic. We had a theory for about 15 years since 1995. And I won't mention it because I think it's wrong. And it's extraordinary that we only in the last year have come to realize properties of these hot Jupiters that suggest a different formation mechanism. And I'll tell you what those properties are. We now find that the Jupiters orbiting close to a star are not orbiting in the equatorial plane of the star, but rather these Jupiters are in highly inclined orbits, tilted orbits. Some of the Jupiters are literally orbiting the wrong way, retrograde orbits. So something like half or so of these hot Jupiters are in these wacky, chaotic, weird orbits. And that has cast doubt on the notion that these are just quiescent, standard model Jupiters. Instead, it looks, in brief, it looks like the best explanation for them is that these Jupiters were scattered gravitationally by an interaction with another Jupiter, maybe two other Jupiters. Several other planets in the system interacted, pulled on each other, yanked on each other gravitationally, slingshotting one of the planets out of the system and leaving the poor surviving Jupiter in a weird, elongated orbit, having survived but now being thrust into this non-circular orbit, bringing it close to the star in some weird inclination, and then trapping that planet near the star. And so it's beginning to look like the so-called hot Jupiters are the result of a sort of gravitational scattering or collision, you might say, that left the survivor in close to the star.
So can you say why those particular systems had rogue planets or nasty planets that were, in a sense, interacting with each other rather than quiet ones?
What happens when a young star forms is that there is this placental material, gas and dust, swirling around the outskirts of the star with enough angular momentum to keep that material fluffed out, sort of like a pizza maker spinning a pizza to flatten out the pizza. Protoplanetary disks are flattened out. And what happens is that planets condense out of that pizza-shaped material of gas and dust, but the planets have no brains, and so they might form too close to each other. If you get one Jupiter forming close to a Saturn, they will orbit for a while in circular orbits, but sooner or later, the Jupiter will come too close to that Saturn. They'll slingshot each other, one of them scattered out of the system, and the other one thrust inward toward the star. And so it's just that bad luck formation when the system forms in an intrinsically unstable architecture.
Something that came up a couple of years ago, a question was asked of Peter Goldreich, a theoretician down at Caltech, and he was discussing this very chaotic system that you have at the beginning when you start making planets. It's a pretty hellish situation. We now have 8 or 9 planets, depending on your personal philosophies. But he was asked, how many planets did the solar system originally have before a bunch of them got kicked out of the nest? And he said, 30 or 40. So we're missing most of the kids.
All right.
Hi. I have a quick question. When, for Doug, I think, when the data goes out into the public domain, do you anticipate that some of the people, including those here in Silicon Valley, would use Hadoop type of technology to attack the big data, or did you have other ideas about how that data might be manipulated?
I would say we hope that you use lots of technologies that we've never heard of and aren't using, because what we really want is, we want discoveries to come out of this data. The project has an approach that we're using that we think is quite good for determining the frequency of planets, but we know, as Martin said, that it misses things, and we know that there are things in our data that our pipeline is tuned to find one thing and it doesn't do so well with this class of things. So I would say, we're certainly hoping to get as much participation as possible, and Martin wants to say more.
Yeah, the additional comment there is that this isn't just stamp collecting. It's not just the pride and the joy of finding a new planet. Our pipeline is designed to find as many planets as possible over a very large statistical sample, and it misses stuff. And the important thing for us to understand is what it has missed. Because only then can we do these calculations which Geoff has referred to, where we can infer the frequency of Earth-sized planets around stars.
Yeah.
And so the job that you guys will hopefully do over the next few years is not only great for you, and not only great for community science and public science, but it is critical to the success of the Kepler mission, and we need you guys to do it.
Okay. That's why I mentioned big data. Thank you.
Good. Mohammed, I'm going to encourage you to come a little more forward. You're sort of prejudiced in favor of the people in the back right now, so after that, come on forward.
Hi. I was wondering if you could now put any kind of rough estimate on the fraction of star systems with planets so that I can write it on my T-shirt here. The F sub P number, basically, in the Drake equation.
How many significant figures do you want?
Yeah.
I'll settle for one.
I heard your question. I'm not sure you asked the question you meant to ask,
Okay.
but I'm going to answer your question and maybe extrapolate a tiny bit. Let me first repeat what Seth said, and I'll embellish it in an important way. We now know, based on not just the Kepler mission, but other detection techniques, that planets are essentially ubiquitous. But let me be a little more careful. It is apparently the case that something like, I'll be very quantitative here, something like 30% Kepler has shown of all the stars Kepler has been surveying, 30% of them have planets of some sort in the very inner regions with orbital periods of 100 days or less. That is to say, inward of even Mercury's orbit, even within that small domain near the star, something like 30% of the stars have planets. A reasonable extrapolation out to orbital periods of 200 days and 1 year where the Earth is and beyond shows that, in fact, there will almost certainly be, on average, more than one planet per star. And I think Seth said it right. There's probably 1 trillion planets or so in our galaxy of 200 billion stars, with something like an average of 5 planets per star. That seems very reasonable to me.
So F should be should then be about 1 in that case.
Sorry?
F should be, the fraction should be about 1 then.
Something like that, yeah. But let me give you one slight twist on it. About half of the stars in the galaxy are binary stars. Of those, some of the binaries are relatively close pairs of stars. And if the two stars are close enough, that is to say something like an Earth-Sun distance or a Jupiter-Sun distance apart, if those two stars are too close to each other, they will gravitationally scatter the planets out of the system, even if it's lucky enough that the planets formed at all. So those binary stars that are close probably do not have planets. And that's why the real number is something more like 70 or 80% of the stars in the galaxy probably have planets. The remaining 20% are in close binary systems that are not suitable for planets.
But Tatooine is possible, right?
And in particular, we're finding more and more so-called circumbinary planets, planets in which they orbit the two stars. The two stars are orbiting so close that a planet can be outside them and orbit in a stable way.
This question is for Seth. It's a multiple question. How many telescopes do you have at the Allen Array? And since you're looking at the Kepler field, which is very broad, are you narrowing it down, and what is your decision on how to narrow that down? And then how long do you look at a particular area before you move on?
Yeah, well, I'm glad that Jill Tarter came into the talk back there. I think that's you, Jill, right? How many telescopes at the Allen Telescope Array? Well, I guess you should say one, but that's kind of insisting on a semantic point. The number of antennas is 42 at the moment. The design goal was 350. So we can go from 42 to 350 with your checks. So that point has been made. But in terms of what we look at, the entire list is in there. Joe, correct me if I'm wrong on this, but the entire list is on there. And we look at any particular star system at any particular frequency. And one of the big advantages of the Allen Telescope Array is that it can look over a very wide range of radio frequencies. That's a kind of an experiment for SETI that is new, really. That is generally not done. But in any case, at any given spot on the dial, any given star system, typically you're talking about integration times of a few minutes. Okay, so ET has that window of opportunity.
So, hi. Seth mentioned earlier that the Kepler field is fairly far away for SETI research. It's, I think, about 1,000 light years for those stars. Are there any plans for like a follow-up mission to Kepler that would look at, say, closer stars that we would be much more likely to detect radio frequencies from?
There's more than one set of plans, I'm sure. There's one in particular that I know about, which is called TESS, which is transiting Earth-size, or I forget what that stands for, but it's basically going to survey the entire sky for nearby objects looking for transiting small planets. And it's a Kepler-like in that it's looking for transits, but it's got multiple cameras, so it has a wide field that way, and it'll be in an orbit around the Earth where it's going to eventually scan the whole sky. So that'll do a survey of the nearby planets, which then you could do some more follow-up with larger telescopes.
Can I make an important point here, by the way? Keep in mind, finding a habitable world or 10 habitable worlds or 100 habitable worlds, as I tried to imply, that could be very significant for SETI in terms of getting the funding and stuff like that. But in terms of finding ET, it's maybe not that significant. Keep in mind that if Earth, if the Earth is destroyed here at the end of the year, as we heard it will be, then it had a run of 4.5 billion years. The amount of time that it was broadcasting detectable signals has been maybe 60 or 70 years, right? So that's a very tiny fraction of the age of this planet, right? So if you could have looked at the Earth for most of 4.5 billion years and not picked up anything. So getting a handful of habitable worlds, that will make big headlines, but that doesn't solve the SETI problem. What you want to do is to be able to look at lots of star systems.
Okay, we're going to have one more question from the audience, and I'm going to give the panel a chance to say a few closing words. Who's got the last question? Right there.
So if there are trillions of planets in the galaxy, and there are billions of planets that potentially could support intelligent life, some people have taken that to mean, well, gosh, given that the galaxy is not currently teeming with intelligent life, because we probably would have just noticed it, does that sort of indicate that maybe we should be skeptical or pessimistic about the future of intelligent life in the galaxy, that somehow, even though there are billions of planets for it to arise on, there doesn't seem to be a lot of civilizations out there?
Oh, okay. Do you want me to go? Do you want to go?
It depends on, do you want to hear the white hat first or the black hat?
The black hat's always more interesting. You ought to go second. Should we be pessimistic? My answer to that is no. And for the reason that I just stated, right? The total number of star systems that have been looked at carefully is, a few thousand in a galaxy of a couple of 100 billion star systems. This is completely equivalent to you looking for megafauna in Africa that can pick up peanuts with their nose, right? Suppose you go to the west coast of Africa, you look at one city block of Africa, you say there are no pachyderms here. That's it, Bob, right? That would not be a very good experiment. That's what SETI has been able to do so far. But SETI is increasing in speed thanks to improvements in technology. So, hold on to your hat, but white or black. So I don't think it means anything. You should not be pessimistic.
I'm pessimistic.
He just told you not to be.
I'm kidding a little bit. You cannot doubt that there's intelligent life in the universe elsewhere. And the reason is implicit in the nature of your question. There are hundreds of billions of planetary systems within our Milky Way galaxy, any one of which might spawn technological life. And there are hundreds of billions of galaxies within our universe, all of which have hundreds of billions of planetary systems. So the number of biological throws of the dice is just too large for our universe to not have intelligent life, and probably intelligent life by the thousands, the millions. But the real way to ask the question and try to answer the question is, how common is intelligent life? How far do we have to travel, essentially, to find the nearest intelligent neighbor? Is it 5 light years? Is it 100 light years? Is it 1,000 light years? How many intelligent civilizations are there within our galaxy? Is it a dozen, 100, 1,000? Exactly what is that number? And I think that you asked the question in a way that makes SETI even more exciting. We don't know. We don't know the density of intelligent civilizations. We don't know how many intelligent civilizations there are per cubic 1,000 light years. And because we don't know the answer, I think that's what makes SETI science. If we knew the answer and we were just sort of waiting to discover them, well, then there wouldn't be any mystery. But there is a suggestion, as you said, that the galaxy may not be teeming with intelligent civilizations. And so it begs the question, are we humans one of thousands of intelligent civilizations in the galaxy, or are we one of a dozen, or maybe only one of a handful? And only by searching will we find the answer.
Well, that's a good place on which to begin to conclude. Let me give each panelist a chance, if you wish, to say something in conclusion. Shall we start in the reverse order? This time number 4 goes first.
Now I really don't have anything to say. So, just indulge me, we talked about the ability of the public now to find brand new planet candidates using archived public Kepler data. Would you put your hand up if you're going to have a look?
Hey, look at that.
Woohoo. All right. That's about 20% of the population.
I think actually Geoff gave you the bottom line, and it's this, that you really do have to look. I mean, 300 years ago, people were still speculating about Terra Australis Incognita. Was there a big landmass at the bottom of the Earth? And you could have sat in the bars of Europe and discussed this till wee hours of the morning, drinking a lot of beer. And there were good arguments you could make on both sides. I mean, there are a lot of land masses on the Earth, and so why not one at the bottom? But in the end, what you really needed to do was build a ship and sail it.
Well, I guess in my closing thought, I would say, in my quiet moments, I think about Tanzania and Ethiopia and East Africa in general, and to think that just 2 million years ago, blink of an eye in Earth history, we were living in the trees, and the Australopithecine somehow had the driver to amble out onto the East African savanna, take chances against the cheetahs and the wildebeest. And we've made it this far, now covering the Earth with our culture, our music, our art, our vision, and with remarkable technology. We've achieved something that I think we should all feel very proud of. It's an amazing species. We're scrambling. We're frankly not that smart. We make a lot of mistakes. But look how far we've come. And I think the real question, because of that remarkable achievement, the question of SETI is even more beautiful. We're really trying to find out if any other species out there had something like the success that we've had so far.
Well, I'm not sure how I'll top any of this, so I won't even try. I'll basically want to get back to just the Kepler mission, and it's, as people have said, people have been speculating for hundreds or thousands of years about whether we're alone, whether there are innumerable worlds like ours. And a group of people, funded by a group of people like you through the US government, got together and designed an experiment that can answer that question. We're going to look and we're going to find out the answer. And it sort of gives me optimism that in spite of all what the craziness that's going on and everything in the government and wherever, we can still do this and we can do things like this. And I think SETI is another example. If we want to know if there's intelligent life, we can sit here and speculate and drink beer, and I'd be happy to do that with Seth. But if we want to know, we need to look. And it's with any other things. Do we want to know about the atmospheres of these planets? Well, we have to go and answer the question ourselves. So I think Kepler is a step in this process, but it's sort of an example that we can do things like this, and it's good, and it's encouraging.
So I would like to suggest a last thought, which is that I've been teaching astronomy since 1973, and for most of that time we said, we don't know whether there are any planets out there. That's one of the unsolved mysteries of the universe. And it's remarkable for all of us to be alive at a time when we've made the step from not knowing about planets out there to actually not just knowing they are out there, but being able to characterize them as well as the panel has. In a way, I feel it's like being alive at a time when Columbus and Magellan and Captain Cook were finding all these new places, and you could go and hear them and find out what was being discovered at the very edge, at the very frontier of knowledge. So I'd like to thank our panelists for all the great work they do, for being part of the new frontier and spending a little time with us. Go forth and find planets. Good job, guys.